So here we're going to continue with our equilibrium constant, KEQ, KC, KP. We're going to start talking about different ways to calculate it and what that means. First, we're going to start by talking about a reaction quotient, which is Q. Okay, so Q is the same thing as an equilibrium expression, except we're not sure if it's at equilibrium or not. So if we calculate Q and it's equal to K, then we're at equilibrium. If it's not, then we're not at equilibrium, and our reaction will shift. Okay, so it's the same expression. You don't have to worry about learning how to rewrite this. It's just we're not sure if it's at equilibrium or not. If they are not equal, K and Q, if K is the greater one, the system will shift to the right, shift towards the products. If Q is the greater one, then it will shift to the left, shift towards the reactants, and then it will reach equilibrium. So we're going to start with this problem, okay? We do not know if it's at equilibrium. That's the first question here, all right? So we're going to find Q instead of K. So Q is just the same thing. So we're going to take our reaction up here. It's the concentration of NO2 squared over the concentration of N2O4. And then I'm just going to go ahead and plug in my numbers. So NO2 is 0.55. And N2O4 is 0.12. And when I do that out, squared. When I do that out, I get 2.5. So you can see here, Q is equal to 2.5 and K is equal to 0.21. So it is not at equilibrium. They would have to be equal if it was at equilibrium. So now the question is, which direction is it going to shift? So here our Q is bigger than our K. So if Q is bigger than K, the system will shift to the left. These three dots are there for, we use them a lot in chemistry. So you can say Q is greater than K, therefore shift to left. So that's Q. So now let's talk about what happens if we flip the reaction. So we know that these reactions can go both ways. Okay, get rid of this. So if we were to write this with our equilibrium arrow, it would look like this. Okay, so this is our forward reaction, and this is our reverse reaction. So let's talk about what the relationship between the K values are. So the K value for the forward reaction is this, right? Concentration of C to the third power, concentration of A to the second power times B. Great. The K value for the reverse reaction is this, A squared times B over C cubed. If you look at these two, they're the inverse of each other. If you're not familiar with the word inverse, it just means you flip a fraction over. So if you take this and you put the a squared b on top and the c cubed on the bottom, you get this. What's nice here is that we wouldn't have to do all of this work if we have a k value for a forward reaction, which if it's not specified, that's what's given to you. Like if it says for this reaction, KEQ is this, that's for the forward reaction. If you wanted to know it for the reverse one, you would just inverse it. So put 1 over that number. So this right here is a very useful relationship that we can have. So now let's talk about what we can do with K for stoichiometry. And then we're going to kind of put all this together, right? So if we have, I think my app, when I import the slides, gives those little boxes. So I'm just trying to cross them out as we go along. If we have this reaction, we know that the K value looks like this. We just did it, okay? What if we had this reaction doubled? So if we multiplied this entire thing by 2, we would get 4a plus 2b plus 6c, gives 6c. Our K value would be this right here, which is the same as this. So you would take your original expression, instead of multiplying it by 2, you're going to raise it to the second power, okay? So whatever you do to a reaction, if we tripled it, we would raise it to the third power. Okay, if we multiplied it by 5, we would raise k to the 5th power. All right, so whenever you double a reaction, you're going to take k to the second power. And that's also a great thing to have because you wouldn't have to do out the expression. Like say you had this reaction and you knew k was 4, you know if we doubled it, then k is 16. Okay, and that works, it's not just by multiplying it by 2. Whenever you have n, you're going to raise it to the nth power, raise k to the nth power. So those are both some useful things that we can use. Okay, if we flip a reaction, we're taking the reverse reaction. We take the inverse of k. If we multiply the reaction by a number, we raise k to that power. So let's talk about why that is useful. So first, we're going to talk about something called Hess's law. Now, you might have been exposed to Hess's law in first year chem. My guess is with COVID for the past 2 years, you probably haven't, okay? So I'm going to have a Hess's law practice worksheet for you in class, and I'll go over it briefly here and kind of tie it to K so that you'll be able to use that information. So we're going to use the stuff we just talked about with K and also this rule. When you add reactions, and I'm going to talk about that in just a minute, you multiply K values. We can use Hess's law for a bunch of different values, and we will throughout this year. And sometimes the values are added. For K, for the equilibrium constant, they are multiplied. That's very important to know. For other things that we'll do throughout the year, they are added. Here, they are multiplied. So if you were exposed to Hess's law earlier, you probably did it with delta H and you probably added them. Here, it's K, it's multiplied. All right, so Hess's law, this is really the first time we're doing it in this class, so I'm going to explain what it is first and then tie the K part into it. So we can use this for different things, like as I mentioned, by manipulating other reactions. So let's take a look at what this works, how this works, okay? So here we have this overall reaction, and we have these given reactions. So what usually will happen is that the given reactions will have a value attached to them. For right now, we're not going to worry about that. So like we would have K values, and whatever we did to the reaction, we would then have to change K based on the reaction. Okay, I'm going to get to that later. Right now, we're just working on Hess's law. All right, so here, what we want to do for Hess's law is take these given reactions, which would usually have a number attached to them, and we're going to manipulate them to get this overall reaction. So how you choose to go about that is your business, but here I think the easiest way to do it is find something that's in the overall reaction that only shows up in the given reactions once. For example, CS2. It's only here once, so we can use that. All right, so what you need to do is manipulate your given reactions to eventually add up to this one. So CS2 here, we have one CS2, coefficient is 1. That's the same. But look, CS2 is on the wrong side of the arrow in our given reaction. So what we're going to do is flip this reaction here. So I like to keep track of what I'm doing. So I'm going to say flip. And then I'm going to rewrite it. CS2 gives C. Sometimes the states of matter do. I don't think it does in this one, but they might. Gives me this. So all I did was take our given reaction and flip it around the arrow. Now you'll see I'm going to line up the arrows. That's why I'm doing it kind of spaced out a little bit. Okay, so now we have next in our overall reaction, we have O2, but see how that shows up 2 places? I'm going to skip over that one, okay, because it doesn't really help me. So then I go to CO2. CO2 is right here, and it's the only place it shows up. We have 1 CO2 after the arrow. In our overall reaction, we have 1 CO2 after the arrow. So I'm going to keep that one exactly the same. So I'm going to rewrite it with my arrows lined up. C plus O2 gives me CO2. And then for our last one, we have SO2 after the arrow, and we have SO2 after the arrow. But in our overall reaction, we have 2 of them, and here we only have 1. So I'm going to multiply this whole reaction by 2. So that gives me 2S plus O2, oops, 2O2, plus 2, gives 2SO2 gas. So now what we're going to do is add them together. So what you could do is just add everything before the arrow in one line, everything after the arrow in one line, and then cancel. I think it saves time and energy if we just cancel now, okay? So see how I have carbon before the arrow up here and after the arrow down here? That means they'll cancel. And I also have 2S before the arrow here and after the arrow here. So that means those also cancel. And I think that's all I have for canceling. So now I can take all of this and add it together before the arrow, and all of this and add it together after the arrow. And you can also combine like terms. And by that I mean we'll have CS2 liquid. And then we have 1 O2 here, 2 O2 here. So I'm just going to combine that to 3 O2. And just to be clear, the reason none of that canceled, the O2s, is because they're all before the arrow. In order for something to cancel, it needs to be before in one reaction and after in another reaction. And then we get CO2 gas plus 2SO2 gas. And that is what we wanted. It's our overall reaction. Okay, so once we get the hang of this, we can add that case stuff in as well. But before we do that, I would like you to practice a Hess's law problem. So please pause the video and try this one on your own, and then come back and we'll do it together. All right, so for this one, yep, we can start with NO2. Just making sure NO2 is here, just making sure it only shows up one time down here, and it does right here. So we have NO2 here, and up here we have NO2. So we need to flip this because in our given reaction, it's on the wrong side. We want it on the reactant side. So we're going to flip it. And then we're also, and this happens, we're also going to multiply it by 3/2 because we have 2 here and we need it to be 3. So that's going to give me 3NO2, and I'm just going to leave off the states of matter for this one because they don't matter here. So we're going to give 3NO plus 3/2 O2. Okay, next on my overall reaction, I have O2 before the arrow, and it only shows up in my given reactions one time here. It is before the arrow, but it has a 2, and we want it to be 1. So we're going to multiply this one by 1/2. So we end up with N2 plus 5/2 O2 plus H2O gives us 2HNO3. Okay, so this one is a little bit harder than the last one because here we already did HNO3, it's right here. So now we're at NO. The reason this one's a little bit harder is because NO shows up in 2 places. Okay, so we want to make sure we have 1 NO after the arrow. And we already know that because of this, we have 3NO after the arrow. So you need to kind of use your critical thinking skills to say, okay, if I have 3NO after the arrow because of what I already did up here, how can I make this one? And the answer is to make 2 before the arrow, right? Because then 2 of them will cancel out. So what I'm going to do to this one is take my 2NO and make it before the arrow. So I'm going to flip the reaction. So now I have 2NO, N2 plus O2. And now let's make sure that all works. Okay, so what we're going to do next is add all the reactions together. So I'm going to cancel out anything that I see on both sides. So N2 cancels. And that's it, that cancels all together. But look, we have 3 halves O2 here and 1 O2 here. So that's going to be 5 halves, which we have before the arrow here. So all of those will cancel. We got our 5 halves before the arrow and then our 5 halves after the arrow. And then lastly, we have 2NO here and 3NO here. So this will go away completely, and this will become a 1. So if I rewrite the reaction, I get 3NO2 plus H2O gives me NO plus 2HNO3. And that's what I wanted. So again, we'll have more practice with Hess's law in class because I know it's probably new for a lot of you. What I want to do before the end of this video is just go over about what that means for equilibrium situations. So in an equilibrium situation, let's say we are given our K values, okay? So we're going to do the same thing. Here we have our overall reaction, which sometimes you'll see as net. We have our overall reaction that we need to add these two up to. So let's figure out what we need to do to each reaction for Hess's law, okay? So A shows up in our given reaction one time, and it is a 2A, but it's on the wrong side of the arrow. For our net reaction, our overall reaction, we need it before. So we're going to flip this one. So we're going to do 2A gives us 4B plus C. And then here, C shows up in 2 places. So I'm just going to go straight to D. D shows up just here, but we need to multiply this by 2. So that gives us 4B plus 2C gives 2D. And let's just make sure that's right. We're going to add the reactions together. So the 4B's will cancel. And then this C will go away and we'll end up with just 1 here. So we end up with 2A plus C gives us 2D. Okay. So Hess's law is great, but that's not what this problem is asking. All right, this problem is asking what's K for our overall reaction. That's when our stuff that we learned before the Hess's law part of this video comes into play, okay? You know that if we reverse a reaction, we can do 1 over K to figure out what the new K is. So if you have the K for forward reaction, you then reverse that reaction, you take the inverse of K. So let's see, in our problem, we flipped this one right here. So to find out what our new K would be for this reaction, we would just take 1 over 0.5, which we know is 2. So our K for this new flipped reaction that we used is going to be a 2. So for reaction number 2, we multiplied it by 2. You know from up here that when you multiply a reaction by some number, your K is raised to that number. So if we multiplied this one by 2, then your K is going to be 3 to the second power, which we know is 9. So now we have our two different K values for our new reactions. Last piece of this, which we did before the Hess's law thing, is that when reactions are added, which is what we're doing in Hess's law, the K values are multiplied. Okay? So our new K values, so our 2, because we added this reaction, which was the flipped one, and our 9, because we added this reaction, which was the multiplied by 2 one, are added together. Excuse me. The reactions are added, the K values are multiplied. So your K, and I'm just going to put for net, is going to be your K1 times your K2 as altered. Okay, so don't go back to these numbers. That's not going to work. You have to use the altered versions. So here, it's going to be 2 times 9. So K for this one is 18. Okay, so let's do a couple more of these. So if you feel confident about this and you want to pause it and try it on your own, great. If you don't, you want to watch me walk through it, that's great too. You'll notice there's some temperatures in this one. They're the same temperature. That's just because, remember, the last video we said K can vary at temperature, but it doesn't matter here because it's the same. All right, so let's go ahead and try this one. So for this one, you're given this reaction with this K value, and this isn't a Hess's law problem. We're just like, okay, how does this reaction relate to the one we're given? It's flipped, right? We have 2SO3 gives us SO2 plus O2. So if the reaction is flipped, K is 1 over 261. So that comes out to this. So that's our K value. So here, what's the relationship between B and our first reaction? It is halved. So it's times 1/2, which means it would be K to the 1/2, which also, you know, is the square root of K. So the square root of 261 is 16.2. So that would be our K value. So now we're going to put it all together in a Hess's law problem, okay? So again, you can judge how you're feeling. If you feel like you want to try this, I mean, there's no pressure. You're just doing it alone. Pause the video and try it on your own. If not, it's fine to watch me go through it. So this is a Hess's law problem. Our net reaction is the one at the bottom. And we're giving KPs for the two reactions at the top. So I'm going to start with N2 N2 shows up once up here, and it's right here. They're both coefficient of 1, so that's great. But the N2 up here is after the arrow, so I'm going to need to flip this one. I'm going to write my new reaction to down here because I don't have a lot of room up there. So when I flip it, I end up with N2 plus O2 gives me 2NO. And if you wanted to write a new K right here, you could totally do that. Okay, so if you flipped this reaction, that means your new K is going to be the old one, but in inverse. So 1 over the old one. And for this one, that is going to be 5 times 10 to the 31. So O2 in our overall reaction, we already did. It shows up only here, okay? Br2. Br2 shows up in one place, right here, but it's half Br2. So we're going to need to multiply this one by 2. So we end up with 2NO plus Br2 gives 2NOBr, and our Kp, so K is going to be 4, and since we multiplied the reaction by 2, it will be 4 to the second power. So that's going to be 16. So now I'm going to add the reactions together just to make sure I did this correctly before I mess with the Ks. So the 2 NOs will cancel, and I'll end up with N2 plus O2 plus Br2 gives me 2 NOBr. I check. That is the reaction I wanted. Great. So when you add reactions together, you multiply the K values. So we'll take these two numbers and multiply them together. And so when you do that, you end up with Kp is equal to 8 times 10 to the negative 30. I just went and checked my math because it didn't make sense to me. I forgot the negative sign here. So when you take the inverse of 1 over 2 times 10 to the 30th, you get 5 times 10 to the negative 31. Sorry, I didn't catch that error. So the Kp here is correct. I just forgot to add the negative sign here.